Let's start this lesson on the second derivative with a little bit of a quick exploration. Um, if you have your notes in front of you, we're going to try a quick exercise here. On each of these blank grids, I want you to sketch tangent lines of an unknown curve. And I want you to try to draw it so that the 5 tangent lines start with a negative slope, and then each subsequent tangent line should start to have an increasing slope. I'm going to highlight that, an increasing slope. And in the second graph, I want you to start with something that has a positive slope, and each subsequent tangent line now then has a decreasing slope. So go ahead and give that a shot right now and see if we can come up with a curve that fits those conditions. So for me, for this first one, I'm going to start with a tangent line that starts negative. I'm just going to draw something right around here. And let's just say that at this point right over here, it starts to then kind of go from a negative slope to a horizontal slope. And then after that, it's going to start having, well, let's actually make that less sharp. And then it's going to have a positive slope here. And it's going to increase here. In other words, that slope is going to increase. And here, we're going to see another positive slope that's even more dramatically increasing. So a graph that would look something like this might just kind of look something like this. I'm just kind of sketching something that looks like a curve that does this. So we can see here with this function, this graph is starting to, we have tangent lines that are increasing. We start with negative, and then it went to 0, and it was slightly positive, and then it became even greater in value. Now, what about something that would do the opposite? Something that starts out with a positive slope, and then each tangent line has a decreasing slope. So let's start out with something that's positive. And then here would say maybe it becomes a little less positive, right, or lower in value. And then again, it becomes horizontal tangent line here. And then it's going to start getting a negative slope. And let's make it pretty dramatic there. And if we try something like this now, we can see that this curve would have something that looks something like this here, right? And what are we noticing here? When the tangent line slopes are increasing, what would you think would be true about the second derivative? That is to say, the derivative of our first derivative. Well, if we know that the first derivative describes the slope of the tangent line, the second derivative then describes the rate at which these tangent lines are changing. And let me actually just write that here. The second derivative describes the rate at which these tangent lines are changing. So if the slope's tangent lines are increasing, that then tells us that the second derivative must be positive. It's greater than 0. Let me write this as this. The second derivative is greater than 0. And when the second derivative is positive, we'll notice that our graph is opening up. And a way of describing this is to say that this function is concave up at this point. You can think of concave up, like a cup opening up. Now, what about when those tangent lines are decreasing? Well, when the tangent lines are decreasing, what that means is that our second derivative, or actually, you know what, we know how to write the second derivative by now. The second derivative this time now is negative. That's not to say that the slope is negative. It's the rate at which the slopes of those tangent lines are changing. Those are going to be decreasing. So in this case, we would describe that function as being concave down. So you can say concave up, kind of like a cup, concave down like a frown. I'll even just do that. Concave down like a frown, if that helps you remember that. So what we're describing right now is the way a function behaves, or a feature of a function. We are describing its concavity here. So the concavity is a feature that tells us how the function is behaving. So in a concave up function, we notice that our tangent lines are going to be below the function, as we saw in our previous examples. And in a concave down function, the tangent lines are going to be above the function's graph. Well, maybe we should say graph instead of the function. That might be a little bit easier for us to process. Above the graph, okay? Now, when a function changes its concavity, We call that an inflection point. And let's take a moment to really break this down, the idea of an inflection point. We say the following. If the function has an existing tangent line at a point where the function changes concavity, that point is called an inflection point. So let's break that down for a second. When we say an existing tangent line, we say that f prime of x exists. Now, I'm bringing this up because not everyone necessarily agrees with that. Or I should say, there is not a definitive statement on whether or not f prime of x exists. Some texts do require that the tangent line must exist. Some don't make any mention of it. So that's not to say that they disagree, but they don't make that a requirement for an inflection point. So we are going to proceed with f prime of x having to exist, us being able to draw a tangent line. Although there will be some exceptions to this, a good example of this is something like the cube root of x, which that graph looks something like that. I'm just going to kind of roughly sketch this. The cube root of x does something like this. And I know it's kind of hard to tell with this sketch here, but this point 0, 0 can still be considered an inflection point because it's changing concavity from positive, so concave up, to concave down. However, you'll see here that this, if we were to sketch the tangent lines at this point, we see that these tangent lines actually approach positive infinity. So in other words, we have a vertical tangent line. So under most definitions, we typically allow a vertical tangent line to be a unique tangent line, even though that point wouldn't necessarily be differentiable because the tangent line slope would be undefined. Don't get too worried about that. Don't get too bogged down in that. We are going to proceed with f prime of x having to exist. The second condition is that that function is changing concavity. And similar to us talking about a function changing from increasing to decreasing to be an extrema, we can then look at the following. F prime of x would be equal to either 0 or undefined, and more importantly, and f prime of x changes signs. So this is very similar to our understanding of extrema, where we would look at where that function is changing, where that function's derivative, I should say, is changing signs from positive to negative. When we're looking at concavity, we would say that when the second derivative is either 0 or undefined, if the second derivative does indeed change signs there from positive to negative or negative to positive, then we can describe that point as being an inflection point. So let's take a quick look at a graph here, and let's try to determine the intervals where this function is concave up, concave down, where there may be no concavity at all, aka when the first derivative is constant, and where there might be any inflection points. So let's go through this, and I'm going to kind of color coordinate this as best as I can. So take a moment and look at this graph here. First off, where would we say that this function is concave up? We'll just graphically look at it because we don't actually have a function in front of us. We could say that from -2 to -1 looks like it's concave up. Also from -1, oops, not -1, sorry, +1 to +3. And then also from 4 to 5. So let me actually kind of highlight those regions here. Concave up, this looks like it's concave up, and then also concave up here as well, okay? 1 to 3. Oops, I kind of went too far with this, didn't I? 1 to 3, I apologize, because there's something else going on from 3 to 4. We'll talk about that in a second. And then 4 to 5. All right, now let's look at where this function looks like it's concave down like a frown. We would see it right here. So from -1 to +1. And then also looking like it's concave down from 5 to 6. So right around here. So 5 to 6. And I think we got all of them. Now, let's move on to the next color. Where does it look like where does it look like there's no concavity? Well, where does it appear that the slope is constant? Well, from 3 to 4, it looks like the slope is the same. Whatever the slope is here at 3, at the beginning of 3, is the same. It's not changing. The slope of the tangent line is not changing. So 3 to 4 would be one place. And I know this last one might be a little difficult to see, but actually the function here is meant to kind of be a little flattened out here. So we would also say that from 6 to 7, the slope is constant. Therefore, there is no change in concavity. Okay. Now, finally, where would there be any possible inflection points? Well, there would definitely be an inflection point at 1, 1. So we change from negative to positive, or second derivative changes signs from negative to positive, or we would say that we're going from concave down to concave up, and also at the point 5, 1. So concave up to concave down. Now, some of you might be wondering, let me do this in maybe like something like pink, what about negative 1, 1? Why wouldn't that be a change in concavity? Well, before I put that dot there, if you look at it carefully, in fact, let me actually see if I can erase these. If you look at it carefully there looks like there's a sharp turn. So at negative 1, 1, not an inflection point. And we learned about these sharp turns as being not non-differentiable points. So we are not going to include that as a possible inflection point. There's no tangent line that you can draw there. No tangent line at this point. Now, is there another place where we would say there would not be an inflection point? Well, also at 4, 2. This right here as well, 4, 2. Even though it may appear to have that way, we would see that there is no change in concavity there. Okay, we see no change in concavity to a positive concavity, but more importantly, it's not differentiable there at the point 4, 2. Okay, now let's try this problem here, where we're given a function. So we're not given a graph this time, but we're just given a function. So what we can do analytically is we can find concavity intervals and points of inflection by using a second derivative number line. So what we're going to do, very similar to what we did with the first derivative test, is we're going to use the procedure, kind of what we did in the previous lessons, defining increasing and decreasing intervals and relative extrema by using a first derivative number line. So we're going to do this with a second derivative. So we're going to say the following. So f prime of x, our derivative, is 4x cubed plus 3x squared minus 6x. This second derivative then is 12x squared plus 6x minus 6. So we're now going to set our second derivative equal to 0. So 0 is equal to, and let's actually solve here. Factor out that 6, so we got 2x squared plus x minus 1. And this would be 2x minus 1 times x plus 1. So we can find what we call our potential inflection points, or what I like to call pips. It's kind of a cute name, right? We've got 1/2 and -1. These are my potential inflection points. We're not sure yet if there is indeed a change in concavity, but that's where they would happen because we found where our second derivative is either 0 or undefined. So I'm going to plot these on my number line. -1, positive 1/2. Now, similar to how we did before, let's go ahead and plug in these values into our second derivative, or plug in a number in each of these intervals into our second derivative and see whether or not these values are positive or negative. So if I try a number that is less than -1, you can see here if I try plugging in a number that's less than -1, we're going to get something that is positive, right? So try plugging in something like -2, for example. You would get something that's more positive than it is negative. So we're going to say that this is concave up here, concave up. And I like to do this underneath just to kind of visually show myself that it is concave up there. If I try plugging in something between -1 and 1/2, like 0, for example, well, 0 plus 0 minus 6, well, that's going to be negative. So I can say this is negative, so it's concave down here. And finally, if I try plugging in something greater than 1/2, like 1, 12 plus 6 minus 6, well, that's also going to be positive. So this is also concave up. So we can say the following, kind of go down the line. We know that our function is going to be concave up from -infinity to -1, and from 1/2 to positive infinity. We can say that our function is concave down from, concave down from -1 to positive 1/2. Now, where do we see no change in concavity? Well, there was no indication that there was any place where f double prime uh, did not change, so we're just going to say none here. Okay, and then finally, where were there any places where our inflection points occurred? Well, we see that there was an inflection point here and here. So to actually find the inflection points, remember we want to list them as coordinates, so we're going to plug -1 into our function. So when we plug -1 in, we should get negative, let's see here, -2, I believe, as an output. And then at 1/2, let's see here, that's going to require a little bit of thinking, and that gives me 7/10. So we found the actual inflection points at these coordinates because, one, we were able to draw tangent lines, or f prime of x existed at those points, right? And then secondly, we saw that this also was where there was a change in concavity from concave up to concave down, or the other way around. So those were our inflection points. And we'll put all this together in our test for concavity in our next lesson.